We're going to talk about another type of uniform motion problem or distance problem. Let's refresh on the two that we've done so far. Now, distance equals rate times time, and we've looked at different ways of solving these distance problems. The first way we looked at is when the distances of 1 and 2, or A and B, X and Y, whatever you want to call it, are equal. So maybe they're going opposite directions. However, the distances are equal. Maybe they're going the same direction, same place, just a different time. Distances still remain equal. One we've done recently, our second distance type of problem, was where we had one distance going part of the way, another finishing it off, or the second distance finishing it off. Maybe you rode a horse, then walked the rest of the way, but the total distance is 100. Therefore, our distance 1 plus distance 2 would equal 100, the sum of the distances. Maybe they're going the opposite direction, meet in the middle, or maybe they meet in the middle and go opposite ways, but all of them have the whatever distance it may be. Ours is 100 in these scenarios. We would use the formula of distance 1 plus distance 2 equals 100, and then obviously that would break down to rate times time, and both of them to equal it so we could solve for our variables. The third one we're going to talk about, this is the one we're going to work on today, is say we have the first distance covering part of the ground, and then the second distance covering the whole traveling or whatever, the whole distance, total distance. Well, what we could say is distance 1 plus what's missing, and it will tell you what's missing, in this case 40. Distance 1 plus 40 would actually equal distance 2. Or it could be written this way: 40 plus distance 1 equals distance 2. So hopefully that makes sense there. And then we can break that down to be rate 1 time 1 plus 40 equals rate 2 times time 2. So let's look at one example of these types of problems and see if we can find some clue words. Let's read it first. Millicent began the journey at 6 a.m. at 50 kilometers per hour. Beauregard began to chase her at 10 a.m. at 60 kilometers per hour. Sounds like a creepy story that should be on Fox News. What time was it when Beauregard got within 40 kilometers of, I abbreviated her name, Millie. We're on a first name basis. She didn't want to be called Millicent. So let's look at some clue words when we read this problem. Millicent began the journey at 6 a.m. Okay, we're going to need to know this is going to be a time. 6 a.m. refers to time. Went at 50 kilometers per hour. Okay, well this is going to be a rate because it's referring to speed. Beauregard began to chase her at 10 a.m. Oh, that refers to time. We'll take a look at that more later. At 60 kilometers per hour. That refers to a rate. What time was it when Beauregard got within 40 kilometers of Millie? I want to look at this part. Beauregard got within 40 kilometers. Okay, oh good. How do we write that? Well, it looks like Beauregard has not traveled the whole distance. He's still got 40 kilometers to go. So what this might look like is, just to show a little table or figure, this is the distance of Millicent. She has gone the entire way. We don't know the total distance, but she has gone the entire way, or in relation to Beauregard in this problem. Beauregard, now remember, he starts later. She's at 6 a.m. He's at 10 a.m. So he starts later. but he's only about this distance, and now he's 40 kilometers within Millicent. He's still got 40 kilometers to go before he reaches the point where Millicent is. So our equation here would be like our third one said, distance of Millicent equals distance of Beauregard plus 40. And then we can break that down further. Rate of Millicent, time of Millicent equals rate of Beauregard, time of Beauregard plus 40. Just converting English to math is all we're doing. English to math. So now we know that we need to find rate of Millicent, time of Millicent, rate of Beauregard, time of Beauregard, our four subscripted variables that we always need to find. Let's see if there's any that it just gives us. All right, let's look at our highlights here. 6 a.m. Okay, well that's not a time travel. That's just a time in the day. But it does give us 50 kilometers per hour. So rate of Millicent is 50. 10 a.m. Once again, time in the day. That doesn't refer to how long they've been traveling, but we are given 60 for the rate Beauregard. So he's going a little bit faster, so he is catching up. Now let's look at our times. It gives us Millicent is at 6 a.m. This is Millicent. Then Beauregard is at 10 a.m. 7, 8, 9, 10. Okay. We want to know what time it was when Beauregard got within 40 kilometers. So what time was it? Okay, well, what do we have here? There's different ways you could write about our times, but we do know that the time of Millicent, and you got to be able to look at this and visualize it, but the time of Millicent equals the time of Beauregard plus 4, because Millicent has been traveling 4 hours longer than Beauregard. All right, 1, 2, 3, 4. She's been traveling 4 hours longer than Beauregard, so therefore we could use that as the time of Millicent. Now that we know that, we can plug into our equation over here. Rate of Millicent is 50. Time of Millicent, we said, is time of Beauregard plus 4 equals 60 TB plus 40, and then you can solve. We'll see if I can fit this down here. Order of operations is to multiply before we add anything, so we multiply by distributing. 50 TB, that's 200, equals 60 TB plus 40. We've got 2 TBs here. Let's combine those. Subtract 50 TB and get 10 TB plus 40 equals 200. Let me move that over here so you can see it. Let's see. 200 equals 10 TB plus 40. And we're just doing the easy algebra part of this now. Minus 40 minus 40. 160 equals 10 TB. It's pretty cluttered, but it's okay. Divide 160 by 10. Divide by 10. Cross out 10. Divide by 10. And you would get 16 equals TB. That got really, that got out of control. 16 equals the time of Beauregard, though. Sorry for the sloppiness. Ran out of room. and camera space. So 16 is the time of Bo. That would mean the time of Millicent would be 16 plus 4, being 20. Okay? So what time, let's see, what time was it when Beauregard got within 40? So time of the day, so we simply got to, let's look at Beauregard. He traveled 16 hours, okay, from this point. Well, okay, let's go ahead and fast forward 12 hours. That would make that 10 p.m. And then add 4 more hours. It would be 2 a.m. Nothing good happens at 2 a.m. So this sounds like a creepy story. Anyways, 2 a.m. would be the time of the day when Beauregard caught Millicent. That's a lot of chasing. Anyways, that's how you do these uniform motion problems. Just look for clues within the word problems.